Hello students, in this video we'll discuss surface integration. If we're given a parameterized surface, S, I'm just going to write down its parameterization. It is R of u and v, and a scalar function f of x, y, and z, which we'll call w. We define the integral over the surface of f of x, y, z d sigma. Now d sigma is my surface area element. This is my surface area element. And what this will be, by definition, is the surface area element is just the integral over the parameterization region. So this, of course, corresponds to u and v residing in some parameterization region D. It's a double integral over D, the parameterization region, of what? Of the function evaluated on the surface times ordinary multiplication RU cross RV, the term we see in our surface area calculation, du dv, and now it's just an ordinary two-dimensional integral. So in other words, we plug in the parameterization to the function, and then we multiply that by the length of RU cross RV, which is your surface area element. Okay, so this over here is called the surface area element too. Surface area element, that's our d sigma. Okay, that's our d sigma. That's what d sigma is in terms of the ordinary standard area element. Okay, it's a dilated area element. So let's see an example how we would do this. Let's give an example of a surface. Let's consider the surface. And what I'm going to do over here is I'm just going to draw the surface. So here's the x-axis, here's the y-axis, and then here's the z-axis. What I'm going to do is I'm going to look at this plane in the yz plane, just the unit square in the yz plane. So this is the point 0, 1, 0. This is the point 0, 1, 1. And this is the point 0, 0, 1. This is going to be one part of my surface. That's my part of my surface. I'm going to call that F1. That's my first face of my surface. And the second part of my surface I'm going to consider is the unit square in the xy plane. That's 1, 0, 0. That's 1, 1, 0. And then we have the unit square. So my surface looks like this top half of a chair, right? It's that part of the unit. It's the unit square in the yz plane. It's the unit square in the xy plane. I paste them together at this joint over here. So that's where these two surfaces intersect. I'm going to call this over here face 2. Okay. What I'm going to find now is here's our example. Let's call the surface F is going to be the union of F1 and F2. So F, our surface F, is both those surfaces together, and we get the union of those two surfaces. So what I want to do is I want to find the surface integral over F of just x plus z d sigma. Okay? So what we're going to do is this surface integral is really two surface integrals. It's the surface integral over F1 of x plus z d sigma, plus the surface integral over F2 of x plus z d sigma. Now we can do a little bit of simplifying here, because what do we know on F1? On F1, we know that x is equal to 0. So on F1, on the surface F1, this x over here, x equals 0 on F1. So that's gone. What about on F2? On F2, the z is equal to 0. So on F2, z is equal to 0 on F2. So that's gone. So we've made one simplification based on properties of the surfaces. Now let's parameterize these surfaces. How do I parameterize F1? I parameterize F1 by, well, let's think about this. On F1, you have your y and z being free, but your x is 0. So on F1, you have 0, u, and then v, where here u and v are both between 0 and 1. And so what does that tell you? That tells you that for this parameterization, your RU cross RV will be, well, what's RU? RU is going to be 0, 1, 0, so RU is going to be J. What's RV? It's going to be 0, 0, 1. That's going to be K. So now let's remember what j cross k is. You have I, j, and k. If you do j cross k, you get to I, and therefore we know that I is a unit vector, so we're going to plug in just a 1 here for that surface F1. On F2, what do you have? On F2, you have u, v, 0, because now the z is equal to 0. Same region, 0 less than or equal to u, less than or equal to v, less than or equal to 1. And then what's ru cross rv over here? Well, ru is going to be 1, 0, 0. That's going to be I. What's rv going to be? Rv is going to be 0, 1, 0. That's j. I cross j is equal to k. And yet again, that is a unit vector, so replace it with 1. So now we can finish our calculation by these parameterizations. And so what we can see from this example, even though this region, this surface looks rather complicated, it's actually quite easy to parameterize this region, and finding the normal vectors is actually quite easy as well. And you can see that because what's the normal vector to R1? The normal vector to R1 is going to point directly out of it, right? And that looks like I. What's the normal vector to F2? That normal vector points straight up, and that's k. So we didn't really actually even need to do that calculation. We could use the fact that the unit area, the unit square has a area of 1, and we know what this normal vector does. It points up or it points over. Good. Now let's continue with our calculation. So what's the surface integral over here? This is just going to be the integral from 0 to 1. The integral from 0 to 1. Now on F1, what is z? On F1, z is equal to v. So we have a v times 1, because this has modulus 1, times du dv. That's for my F1 integral. Plus integral from 0 to 1, integral from 0 to 1 of, now on what is x on F2? X on F2 is equal to u. So I'm going to have a u du dv. Over here, the u integral gives me 1, the v gives me 1/2, so I get 1/2 for this first integral, plus 1/2 for the second integral by symmetry, and I just get 1. So the surface integral of x plus z on this chair-like surface is equal to 1. Thank you very much.